So the title is promising a little bit more than I'm actually going to deliver on. So I'm going to present an example of multi-agent dynamic persuasion problem. And it's going to be a very stylized, highly crafted example. One, because it's the only one I know how to analyze, and the other is that it's highly crafted and parameterized so that I can import a lot of observations and ideas from a previous paper of mine, which I think some of you, many of you have seen me present. I'll take a slide at the beginning to sort of remind those of you those observations and results, and hopefully present for the first time to the others those observations, and those are going to feed into. It's going to be I'm going to remind you of a single agent dynamic persuasion problem, and those observations I'm going to feed into the very stylized multi-agent persuasion problem, so that I can quickly jump to some of the new issues that arise there that at least I can get a handle on in this special example. So here is the reminder of that. Of what I did before. So this is a dynamic Bayesian persuasion problem. So there's a principal and an agent. The principal is observing privately a stochastic process. Over time, he's informing the agent about the current state of the process. Okay? And the agent, based on the information he receives from the principal, updates his beliefs about the current state of the process, and the agent takes actions. And the agent's optimal action depends on what he thinks is the current state. The principal cares about the agent's action, and there's a conflict of interest between the principal and the agent, so he's manipulating the agent's, filtering the agent's information over time in order to get the agent to do what the principal wants him to do. Okay? And the leading example is a problem in which there's an action that the principal doesn't want the agent to take. Okay? No matter what the state of the process is, the principal wants the agent not to take a certain action. Okay? But the agent's payoffs are state dependent, and the state is binary. Okay? So initially we start in a state of the world where also the agent doesn't want to take this action that the principal wants to avoid. Okay? But both the principal and the agent know that the state is changing over time, and there will come a point in time when the state transitions to one in which we have a conflict of interest and the agent wants to take this action. Of course, only the principal sees when the state changes. So the problem for the principal is how much information to give the agent over time about the current state. Okay? And his goal is to filter information in such a way as to keep the agent from switching to this undesirable action for as long as possible. Okay? So the optimal mechanism for the principal in this problem is to inform the agent perfectly that the state has changed, but only with a delay. Okay? So the principal is watching the state. At some point, the state switches. The principal sees this. He keeps the agent in the dark for some length of time, and then he tells the agent. And of course, the agent knows that the principal is using this policy. And the length of the delay is timed so that the agent goes along with the principal's recommendation. That is, the agent keeps avoiding the action that the principal wants him to avoid until that moment when the principal says, the state has changed, and in fact, it changed some time ago. And so now you know for sure that the state is such that you want to take this action that I don't want you to take. There's nothing I can do about that now, and he goes on and does that. Okay? In that problem, the transition rate at which the state changes from the favorable one to the unfavorable one is lambda. It's a Poisson process, okay, and lambda is the transition rate. Okay? There's a length of time t star, and this length of time t star, this is the formula here, but what it means is it's the amount of time that it would take for the agent's beliefs to drift upward. Okay? He starts knowing for sure that the state is the favorable one. Okay? suppose he doesn't get any information from the principal, but the agent himself knows that the state is transitioning at this rate lambda. That means as time passes, his beliefs are going to drift upward, higher and higher probability that the state is the one in which he wants to take this action. Okay? The agent is defined by some threshold, P star, this threshold belief, such that if he thinks that the state has changed already with at least probability P star, then his incentives are strong enough that he wants to take the action that the principal is trying to get him to avoid. Okay? There's a length of time T star that it takes for his beliefs to reach that threshold. Okay? Assuming the principal is giving him no information at all, T star is defined as the amount of time it takes for the agent's belief to drift up to that threshold. And T star is the optimal length of the delay that the principal builds into his mechanism. Okay? So the principal waits until the state changes, and then waits another T star length of time, and then tells the agent it's time to switch. Okay? And so I called that the delayed beep. Okay? So the delayed beep is the optimal mechanism in this simple binary state two-action problem where the principal is trying to forestall the change of action in the agent for as long as possible. Okay? So I'm going to now look at a two-agent version of a problem like this, okay? But it's going to be interesting in a number of respects, okay? So first of all, the principal is not just trying to forestall the date at which a single agent switches his action, but there's going to be a complementarity. So he actually cares about the date at which both agents switch actions, okay? And not only that, but the agents are strategic themselves. So each agent's incentive to switch actions is not going to depend just on that agent's beliefs about the state, but also on whether the other agent has switched already as well. Okay? So in fact, the leading example I'm going to talk about is a bank run. Okay? So in this example, the principal is a bank. Okay? And the bank is presently healthy, but everybody knows that at some rate it's switching to being insolvent. Okay, so there's like a banking crisis, and lots of banks are becoming insolvent, and we just don't know about this specific bank, but we know it's just a matter of time before it switches. Okay, and the switching rate is lambda, and the agents are depositors at the bank. Okay, and these agents have to decide when and or if to withdraw their deposits from the bank. And the bank wants to delay as long as possible, not only the date at which each agent withdraws, but maybe even the date at which a bank run happens. And we'll define a bank run as the date at which both agents have withdrawn from the bank. Okay? Okay, and now here is the highly parameterized part. Okay? So I'm going to describe here the flow payoffs of the depositors. Okay? That is their incentive to withdraw as a function of their beliefs, not just about the health of the bank, but also about the action of the other depositor. Okay? So the way that I've set up these payoffs, okay, waiting, that is not withdrawing, is going to give a constant payoff, and I'm choosing the number P star, because this is going to enable me to use these observations here. Okay? And the effect of this payoff function is the following. If a depositor assigns at least probability P star to the following critical event, then he wants to withdraw. And the critical event is either the bank is distressed or the other guy has already run. Okay? So, summarized by these three cells in the matrix. Okay, once that event exceeds probability P star, then the depositor with that belief wants to withdraw. Okay? So that is to say that if I just look at the single agent version of this problem, okay, that event acts as the transition that I was talking about before, and if the principal was just concerned about forestalling the withdrawal of a single agent, okay, then that single agent's threshold is P star, and the principal would like to use some kind of delayed mechanism to try to delay that for as long as possible. Okay? But of course, there are two agents. and each agent knows that the other agent is receiving possibly private signals from the bank. Okay? So for each agent, he needs to keep track of not just the probability of this part of that event, but also the probability of this part of that event. And so the interesting problem is, how does the principal, through these messages sent over time, control each agent's first-order beliefs about the health of the bank, but also their higher-order beliefs about the other agent's beliefs, etc., about the health of the bank, because those higher-order beliefs, through this strategic complementarity, will tend to accelerate the rate at which agents withdraw, and the principal wants to manage that. So a number of new issues arise when there are two agents or more. Okay? The first is that as I mentioned, it's not just the first-order beliefs, but also the higher-order beliefs that matter. The other is that, of course, the players are going to be playing a game with one another. Okay? And given the higher-order beliefs that each agent has about the health of the bank and the other agent's beliefs about the health of the bank and so on, there's still a multitude of predictions we can make about their behavior. That is, there might be many equilibria consistent with a certain information structure. So the two preliminary steps I'm going to have to deal with are, first, sort of talking about the hierarchies of belief and how they feed into the potential actions that the agents might take, and then talk about equilibrium, and I'm going to make an equilibrium selection, which is then going to pin down exactly what action they take out of the multitude of possible actions they might take given their hierarchies. Okay? So, let me just introduce some notation here for belief hierarchies, which I'm very quickly going to dispense with. Okay, so let me just say at the beginning, there's two ways that one might approach a problem like this. Okay, one is to talk about how each agent will respond to his beliefs and higher order beliefs, and then think about the principal managing those beliefs and higher order beliefs. That would be sort of the direct analog of the way I analyze the dynamic persuasion problem in the single agent case. Okay? The other is to think about more like a sort of direct revelation mechanism approach, where the principal just chooses a mechanism which tells the agents when to withdraw. Okay? And then we check whether the mechanism is incentive compatible, and we look at incentive compatible mechanisms and we optimize among those. Okay? So I'm actually going to carry along sort of both ways of analyzing the problem. Okay? The second approach is going to be easier from the point of view of actually describing and verifying the incentive compatibility of mechanisms. But the first way is sort of a more interesting way to interpret it and a better way to understand what's going on and why the mechanism is incentive compatible. Because we'll be able to say, why is it that the agent is withdrawing? Well, it's because he's pessimistic about the health of the bank. He's also pessimistic about the other agent's beliefs about the health of the bank, and so on. So we'll get sort of better sense of how the strategic complementarities are playing a role when we analyze it through the perspective of the higher order belief. So I'm going to try to talk in both ways. All right, so just some notation here. I want to describe the hierarchies of belief for an agent under which the uniquely rationalizable action for that agent will be to withdraw from the bank. Okay? All of the other hierarchies of belief will be compatible with two possible actions. He might withdraw or he might not withdraw, depending on the equilibrium that the players are playing in the game. Okay? So the first step towards talking about equilibrium is to first identify those hierarchies where there's no ambiguity. The only rationalizable strategy is to withdraw. Okay? So here's the set of all hierarchies. Okay, so it's sort of a standard result that any hierarchy can be represented. So, literally a hierarchy is a first-order belief about the health of the bank, and then a second-order belief, which is a belief about the other agent's belief about the health of the bank, and third-order beliefs, and so on. Okay, but as a standard result that any hierarchy can be represented in a somewhat simpler way as just a probability distribution, probability measure, over the health of the bank and the other guy's hierarchy. Okay? So I'm going to talk in that language. Okay? So a hierarchy is a probability measure of this form. Okay, and I'm going to inductively define a set of hierarchies. So the first set is the set of hierarchies under which the probability that the bank is healthy is small. Okay, less than 1 minus p star, yeah.
Sorry, background question. Are we going to allow the bank to send signals to one player that are informative about what the other player has done?
Yes. So right now I'm just describing the beliefs that would induce. Okay? So if I send you a signal and you know the policy that generates that signal, you can immediately infer from the realization of that signal a probability distribution about the health of the bank, a probability distribution over the signal that the other guy got, and therefore a probability distribution about his belief, and so on. And so my signal will immediately induce in you a hierarchy of beliefs. Okay? And among all of the possible hierarchies of belief, I want to divide those into two sets. And you can basically think of the problem as the principal trying to keep the agents out of the set I'm defining as long as possible. Okay? So if you remember the old beeps problem, that set was the first order belief was larger than p star. And the question was, how do you keep them out of that set for as long as possible? Well, now the domain is bigger. It's the set of hierarchies. But there's an undesirable set. And the principal wants to keep the agent's belief out of that set for as long as possible. Okay? So the first ingredient in defining the set is just the set of beliefs, the set of first-order beliefs that the bank is distressed with high probability. Okay? So just look at the notation. This is the set of all hierarchies of the other guy. So this is just the probability, the marginal probability on the bank's health, which assigns less than probability 1 minus p star to the bank being healthy, and therefore greater than or equal to probability p star that the bank is distressed. Okay? And so if the agent's hierarchy belongs to this set, it's a dominant action for him to withdraw. Okay? All right, so rho I2 is the hierarchy in which the probability that either the bank is healthy or the other guy is not in the first set is small. Okay? So, this is the desirable event. Either the bank is healthy or we haven't already concluded that the other guy is withdrawing. It's possible he might be waiting. Okay? So the probability of the desirable event is small. Okay? And so it's second-order rationalizable uniquely to withdraw, and so on. Okay? So we inductively define sets where it's kth order uniquely rationalizable to withdraw, and then I want to define rho I to be the union of all of these. Okay? And so any hierarchy in that union has the property that the uniquely rationalizable action is to withdraw. Okay? And then we have a very sort of simple, warm preliminary proposition which says that, well, there are many equilibria of the game at any point in time between these agents. Okay? But all of them have the property that when the agents' hierarchies are in rho I, they're withdrawing. And in fact, there's one which has the property that everywhere else they're waiting. Okay? And if we wanted to look at the best equilibrium from the point of view of the principal, the one that allows them to forestall a bank run as long as possible, it would be that one. That's the one that has the agents waiting as long as possible. Okay? And so that I'm going to use that equilibrium selection rule. Okay? Of course, there are multiple equilibria, and the worst case for the principal is that the agents coordinate on the equilibrium where they always withdraw because they're always withdrawing, etc. Okay? And there's nothing the principal can do about that. So we're going to look at sort of the best case for the principal using information to manage their incentives, and that's by looking at this equilibrium. Okay?
So I guess this is just as a side comment, because this is definitely not your model, but it kind of makes the Gabriel's comment earlier, which is if, say, they were moving sequentially, then there's a sense in which if you could explicitly provide information about actions, you could, in a sense, forestall some of these miscoordinated equilibria. Or if I know that if you commit as a principle that you reveal whether I ran, I might not run, knowing that the other guy will see that. So it does seem like in another class of models to think about, there's something particularly interesting about explicit information not just about the state, but about the actions of others as well. Because there's a sense in which you allow agents to do their own selection, so to speak.
Okay, I want to make sure I understand the question. So, first of all, the principal is going to have available to him, and I haven't even started to talk about this yet, so there's no reason this should be clear, but the principal is going to have available to him any feasible policy which sends signals according to any probability distribution as an arbitrary function of the past, privately or publicly, correlated or uncorrelated in any way across the agents. And therefore, as a special case of such a mechanism would be one in which the principal sends a certain signal to agent 2 T star periods after agent 1 has withdrawn. And he announces at the beginning that he's using such a policy, and therefore when agent 1 receives the signal, he knows for sure the behavior of agent 2. Okay, that's going to be feasible. Okay, so I want to see if that's addressed, if that's already addressed your question, because I'm imagining other versions of your question. I don't want to answer them.
I guess all I'm saying is that in your world, it's not going to actually matter whether we let the principal, whether we allow the principal to send information about just the state, or to send information both about the state and the actions that have been taken thus far. It will not matter. Is that correct? First, it's a warm-up question. Here you're gonna.
No, for sure it will matter. Okay, so if you look at these payoffs, suppose that the principal tells agent 2, the bank is healthy, but agent 1 has withdrawn. That will induce agent 2 to withdraw.
No, what I meant is he doesn't actually gain anything. We're going to have a result.
Okay, so it's going to turn out that the principal will be able to, that the strategic complementarities will not be costly to the principal.
And I guess all I want to say is there's a sense in which if you don't start with the equilibrium selection that you have,
yes,
and people are moving sequentially, then there's a sense in which it can be real benefit a strict benefit to being able to provide information directly about the actions of others in the optimum, because you can kind of kill off some equilibria where they're coordinating or not acting by pointing out that they haven't. But you can just, it was really a...
I mean, my guess is that this problem that you're hoping to address is going to be a plague. That is, even if you tried to do that, there will be another equilibrium where the agents just ignore you. The agents just, their strategy is to just withdraw because they always assume that the other agent is withdrawing. And because that's true, this signal is off the equilibrium path. It has zero probability.
But usually sequential moves get rid of some of this coordination problems, right? And then it really would matter. But maybe that's... Because I'm just thinking, if you really want to think of bank run as an example, like it seems to me there is a lot of sequential moves there, and kind of one thing that you might want to talk about is, one is revealing financials, but the other thing kind of revealing, look, other people are not running. And if I can really credibly show that people are not running, then I kind of know, well, if I don't run, the other people will see that I haven't run, and they will not run, and therefore I won't run. So I can kind of, as the agent, as the depositor, kill off the bank run if the bank's committed to reveal, because the other guy can't ignore that I haven't run, because he'll know for a fact that I haven't run, and I'll know that.
Okay, so just for the benefit of those people who haven't seen me present this already, that is part of the feasible mechanism. It's just turned out it's not going to be part of the optimal mechanism. It will be feasible for the principal to inform agent 1 about the behavior past and possibly future of agent 2, but as it happens, the principal will be able to do better than that. And so I think that's sort of the spirit of your question. Yeah? Okay. Okay, so I want to describe a couple of mechanisms just to get a sense of the problem, okay, and to sort of warm up and build up to characterizing the optimal mechanism. A natural starting point is to think about what is the sort of direct analog of the solution to the single agent problem in this two-agent problem, okay? So the single agent problem, I told you the optimal mechanism is a beep with a delay, okay? one interesting issue that comes up when we think about mechanisms in the multiple agent problem is, will they be private messages sent to the agents or will they be public messages? Okay? One try is to take the optimal single agent mechanism and use it publicly. Okay? That is, once the bank becomes insolvent, the bank waits a length of time t star and then publicly announces the bank is insolvent. Okay? So that mechanism is incentive compatible in the sense that the agents will wait until they hear the announcement before they run. Okay? That's pretty straightforward, but I just want to go through why sort of slowly, because it's sort of a setup for the somewhat more subtle incentive compatibility verifications that come later. Okay, of course, because this is the optimal single agent mechanism, it follows that each agent, before he hears the announcement, and therefore is expected to wait, believes that the bank is healthy with sufficiently high probability that he's willing to do that. Okay? But now there's this extra issue that the other agent might be withdrawing. But in this mechanism, because the agent's signals are perfectly correlated, it's a public signal, when each agent is still waiting to hear the announcement, he knows that the other agent is also waiting to hear the announcement. So in fact, it's common knowledge at each of those moments that both agents assign a probability less than p star to the bank having become insolvent. Okay? And so we're firmly inside that set, or outside that set rho I. It's common knowledge that we're waiting is a rationalizable action. Okay, and so that means that the principal can get the agents to wait exactly as long as he can get the single agent to wait in the single agent version of the problem. And there is that time. Okay, I didn't say this before, but the expected time that the principal can get the agent to wait before withdrawing is, well, for sure he gets t star length of time, because that's the length of the delay. Even if the bank becomes insolvent at the very first instant, there's going to be another t star before the announcement comes out. But actually, the expected arrival time before the state transition is 1 over lambda. Okay, so this is the expected delay. Okay, so suppose that the bank was only concerned about the event that both agents have withdrawn. Okay, then this would be, this would be the value of this mechanism for the principal. Okay, now I didn't say explicitly what the principal's payoffs are, what the bank's preferences are. We could imagine a situation where the bank wants to forestall the withdrawal of agent 1 and also with the withdrawal of agent 2 and also the date at which both agents have withdrawn. Okay? I'm not going to say specifically what the principal's payoffs are, because when I describe the optimal mechanism, it'll turn out to be optimal under any specification of those payoffs, provided that withdrawal is a bad thing for the bank. So he doesn't want agent 1 to withdraw, he doesn't want agent 2 to withdraw, and maybe he's got some payoff, some disutility of having both agents withdraw, which is larger than the sum of the disutilities of each individual agent. Okay, it's not going to matter. The optimal mechanism is going to be optimal for any payoff function of that form. Okay, but for this problem, they're all bundled together. Okay, agent 1 withdraws at exactly the same time that agent 2 withdraws. Okay.
Is that going to include he doesn't mind if exactly one agent withdraws?
So a special case would be a problem in which the principal could care less when when a single agent is withdrawn. He's just trying to hold off the date at which the second agent withdraws. So I'll call that a bank run. Okay, so that's sort of the interesting case, but the payoffs can be flexible. Okay, so private messages can do better than this. Okay, and let me just give you some intuition, the intuition for sort of the key benefit of private messages. So we already knew that this is the maximum time that an individual agent can be induced to wait on average. So let's just say that a mechanism is individually optimal if it induces each agent to wait on average, that long. Okay? So in particular, the public beep mechanism is one example of an individually optimal mechanism. Let's talk about the random times at which agent 1 and agent 2 withdraw under some mechanism. Okay? So under whatever the mechanism is, there's some random time at which it induces agent 1 to withdraw and agent 2 to withdraw. And let's denote it by R tilde 1 and R tilde 2. If the principal is concerned about a bank run, that is the date at which both agents have withdrawn, then he's interested in this. Okay? He wants to maximize this. He wants to maximize the date at which the second guy withdraws. Okay? So if I have a mechanism which is individually optimal, so in terms of the marginal distributions of R tilde 1 and R tilde 2, it achieves that in expectation. Okay? But if the principal wants to avoid a bank run, then he wants R tilde 1 and R tilde 2 to be uncorrelated as possible. Okay? Because the less correlated they are, the larger will be this maximum. Okay? To make them, by making them less correlated, the gain he gets is that when agent 1 withdraws early, agent 2 withdraws later. And so the time at which the bank run happens is later. Okay? So the problem with the public beep is that there's the perfect correlation between R tilde 1 and R tilde 2. So the benefit potentially of private mechanisms is that it can make these variables uncorrelated. Okay? The issue, of course, is that there's a limit to how uncorrelated they can be. And the reason is that those R tilde 1 and R tilde 2 are the time at which the agents choose to withdraw. So they come from the agent's beliefs about the state. So they're correlated with the same variable. Okay? So there's only so much uncorrelation the principal can induce in R tilde 1 and R tilde 2. And one way to think about how to approach this problem is to say, let's look at all mechanisms which are individually optimal. Okay, so which do the best you can on the margins, R tilde 1 and R tilde 2, and look at the constraint and try to identify the constraint on how negatively correlated variables can be within that class. Okay, that's sort of the hopeful way to address this problem. Okay, sort of the fear of doing that is that perhaps it might not be optimal to use an individually optimal mechanism. In principle, there might be a trade-off between the margins and the correlation. Okay? So as it's going to turn out, there will be no trade-off. Okay? And so this is sort of partly the answer to the question of why it's not going to matter what the principal's payoffs are.
If the principal wants to maximize the min of R tilde 1 and R tilde 2, then public is optimal?
Yes. Okay. Yes. Although that's an interesting question. That's a very different question for one thing, because then my equilibrium selection really is kind of not, it's sort of working against the principal, right? If the principal wants a bank run to happen immediately, okay, then his preferred equilibrium is the one in which they withdraw right away. Okay? Although, it's still an interesting problem because, we could then ask what's the...
So he's a maximize the min.
I want to maximize the min. So he doesn't want to. He doesn't want people to withdraw.
I see.
But the first guy withdrawing is really painful. The second guy withdrawing is less painful. You're trying to still maximize the min. You're not trying to minimize. In other words, you have a concave cost of how many people have taken out. Then your selection is still good for the principal.
Yes.
And public is optimal.
Yes. It seems to me, I haven't analyzed that problem, but it seems intuitive that would be, yeah. Okay, so the task here is to, one, characterize this constraint, and then show that, in fact, you can't do better by moving outside of the class of individually optimal mechanisms. Okay, and so the optimal mechanism will be an individually optimal mechanism which achieves the bound on this negative correlation. All right, so let me first show you how to construct a mechanism which is individually optimal but not perfectly correlated. Okay, so individual optimality so far meant a delayed beep. Okay? But if I give both agents the delayed beep, I'm making a perfectly correlated mechanism. Okay? They will both hear the beep T star moments after the bank run, after the bank becomes insolvent. Okay? So I need to come up with another kind of mechanism which achieves the individual optimum, but which is not the delayed beep. Okay? So I want to describe for you this other mechanism. Okay? In fact, there's lots of them. All right? But here is the key sort of variation on this idea, which I'm going to couple with the delayed beep to create a two-agent mechanism which is individually optimal but not correlated. Okay? So it works like this. The principle waits until T star. T star, remember, is how long it takes for the agent's belief about the health of the bank to reach the threshold. Okay? After T star, he's informed immediately if ever there is a change in the state. If ever the bank becomes insolvent after T star, the agent is informed immediately of that. That is, he's always kept in the dark about the first 0 to T star interval of time, and after that, he's informed immediately. Okay? So the idea here is that the delayed beep always kept this window of time of length T star in the immediate past that the agent was uninformed about. And the key feature of the length T star is that that's how long it takes for your beliefs to drift up to P star. So if you're always uninformed about a window of time of length T star, okay, then your belief will be, well, the state change has happened with probability P star. Okay? And the idea is to make the window now the initial 0 to T star. Okay? Now that by itself doesn't quite work. Okay? And the reason is that after a lot of time pass, if this agent who's been given this mechanism, who knows he's not hearing anything about the first 0 to T star, if he hasn't heard any beep, he's going to start to think that the reason is that actually the state actually changed between 0 and T star. And so his beliefs are going to move up past the threshold. Okay? So I need to augment the mechanism in order to counteract the natural drift in the agent's beliefs. Okay? And so what I'm going to do is I'm going to have the principal at time T star start an auxiliary Poisson clock, which has parameter lambda. Okay? And when that clock sounds, if in fact the state had changed between 0 and T star, he informs the agent. Okay? The effect of this is that the agent knows that beeps are coming from one of two possible sources, but at the same rate lambda. So the lack of a beep is uninformative about which of these clocks is active, about which of these sources is active. Okay? And so he remains equally uninformed about that initial length of time between 0 and T star. And so this implements the same path of beliefs that the delayed beep implemented. Namely, the agent's beliefs trend upward to P star. They hit P star at exactly time T star, and then they remain at T star. They remain at P star forever until a beep sounds, at which point they jump to 1. Okay? And that's why it achieves the individual optimum. So this would be another way to get the T star plus 1 over lambda value in the single agent problem. Okay? So one thing you could do is you could give this mechanism to agent 2 and give the delayed beep to agent 1. And now you have an individually optimal mechanism, and their run times are not perfectly correlated. Okay? They're not perfectly correlated because, for example, if the state changes after T star, agent 2 finds out immediately, agent 1 finds out T star moments later. If the state change happens before T star, agent 1 finds out T star moments later, and agent 2 finds out some random time after T star. Now, we have to show that this mechanism is incentive compatible. That is, the goal is to show that the agents will wait until they hear the beep and then they will run. Okay? And of course, that works from the point of view of a single agent, but now there's the strategic complementarity. Okay? And in particular, each agent knows that because their beeps are not perfectly correlated, even though I haven't heard a beep yet, it's possible that the other guy has run. Okay? And if I knew he had run, I would want to run, even though I think that the bank is healthy. Okay? So we need to check that the higher order beliefs are outside of the undesirable set. Okay? And the key observation is that both of these mechanisms have the property, and in fact it's a feature of any individually optimal mechanism, that the signal which induces one agent to run is actually perfectly informative that the bank is insolvent. What that means is that agent 2, remember, he's thinking about this critical event, which is either the bank is insolvent or the other guy has run. But the event that the other guy has run is a subset of the event that the bank is insolvent. So the total probability of that critical event is just the probability that the bank is insolvent. And so by controlling that probability, we actually control all of the hierarchy of beliefs in one step. Okay? And therefore, as long as the first order beliefs are below P star, okay, it's incentive compatible to wait, and by our equilibrium selection, the agents wait. Okay? But of course, the moment that they hear a beep, they know that the bank is insolvent, and so they run. It's insolvent. With the Lamppost mechanism, there are two reasons you might run. One is that the state just changed after T star, and you're informed of that, but you're informed that the state just changed, so for sure the bank is insolvent. Or the state changed between 0 and T star, and it's this auxiliary clock that's active, but of course that means that the state changed between 0 and T star. Okay? The two Lamppost mechanisms would do worse than this, of course, because after T star, their run times would be perfectly correlated. Okay? All right. So this mechanism is individually optimal, and the run times are not perfectly correlated. So it does better than the public beep mechanism, again, under the assumption that the principal likes bank runs worse than the sum of the individual disutilities. But it's not optimal. Okay? So it's possible to do better. So the reason is that this auxiliary clock was serving one purpose, okay? But that purpose only constrains it in one way, and there's freedom to specify its correlation with the other variables to get more negative correlation. That's what we're trying to get out of this, okay? So in particular, the clock is there to make sure that this guy, agent 2, is not having his beliefs drift above P star when a lot of time passes. Okay? The key condition of that is that the distribution of beep times that it induces, okay, so let's call that distribution, of course, it's the constant T star plus the random clock time. Okay, so this is the distribution of time, this is the random variable that is the time at which this auxiliary clock sounds. The key requirement is that that's exponentially distributed, okay, that it's Poisson with parameter lambda. Okay, that was all we needed of this clock. Okay? So what we can do is we can design a random variable phi with that property, but tailor its correlation with the other variables. Okay? So here's the idea. So first of all, here's just like a basic observation. So this is a characterization of exponentially distributed random variables. So a random variable, what is this? Is this psi? Okay. A random variable psi is exponentially distributed with the parameter lambda if and only if there's a uniform random variable, u, on the unit interval, such that psi can be written as a transformation of u, this transformation of u. Okay? So what I want to do is I want to construct a uniform random variable from the other variables in the problem, and define psi in terms of that. Okay? And the goal is to make it negatively correlated with the other agent's runtime. Okay? So the variable I'm going to look at is the random time at which the state changes. So let phi, that's phi, right? Phi be the random time at which the state changes. Okay? And let's look at the event that phi happens before t star. That is, after all, when the auxiliary clock is going to be active. Okay? And let's look at this random variable. Okay? So this is the CDF of phi. Okay? So, of course, the CDF of phi is a variable that takes values between 0 and 1. Okay? But conditional on phi being less than t star, it takes values between 0 and p star. Okay? Because the probability that phi is less than or equal to t star is p star. Okay? The probability that there's a state change before that time t star is p star. That was the definition of the relation between t star and p star. So this random variable takes values between 0 and p star. And therefore, if I divide by p star, I get a random variable which takes values between 0 and 1. And it's uniform because this is the CDF. Okay, so we're saying, what's the probability of an event which has probability less than or equal to p star? Okay. So this is a uniformly distributed random variable in the unit interval, and I'm going to use that as my u. Okay? Notice that the effect of that is to make psi negatively correlated with phi. Okay? And since phi is positively correlated with r tilde 1, the time at which the other agent runs, I'm getting more negative correlation. Okay? In fact, the other guy's runtime is just, the other guy has the delayed beep, so the other guy's runtime is just phi plus t star. Okay? So that's the optimal mechanism. Okay, so here, just a summary, here is the mechanism. And now I'm just going to be describing it in sort of direct revelation terms. This is the time at which the principal tells the agents to withdraw. Agent 1, run at a time t star after the date at which the state changes. Agent 2 runs exactly when the state changes, if that happens after t star, and according to this formula, if the state changed before t star. Here's a picture of the mechanisms. Okay, so here is the random time at which the state changes. Here are the run times of the agents plotted here. Okay, so here is r tilde 1. This is a picture of r tilde 1, and it's just phi plus t star. Here's a picture of r tilde 2. Okay, so after t star, it's just phi, and before t star, it's this formula. Okay. Okay, so the shape of this is, in fact, uniquely defined. This formula is uniquely defined by the condition that the distribution induced on t, or r tilde 2, from the fact that phi is random over this interval, and r tilde 2 is a function of phi, is exponential with parameter lambda, and that this is a decreasing function. Okay? And so, in fact, I think I skipped over that statement. This is something from copula theory. Okay, so it's a part of probability theory which says, suppose you have two random variables. Okay, and you want to construct a joint random variable which has the same marginals as the two you were given, and you want to look at the range of joint distributions in terms of like correlation or different measures of correlation. Okay, there are bounds. Okay, and so this is a lower bound, and it's the Fréchet-Hufting lower bound. Okay, for this guy who's for agent 2, he always knows that if the bank has become insolvent and he hasn't found out about it yet, it happened in some interval of time. Okay, that is surrounding the time t star. Okay. All right, so the important thing about this picture is that the blue upper envelope, like if the principal was just trying to forestall a bank run, defined as the date at which the second agent runs, we want to look at the higher of these two. For any phi, we want to look at which runtime is later, which runtime is farther up in time. And the blue indicates that. Okay? And the thing that you can see from that, and just graphically, it comes from the fact that I have a strictly decreasing segment here up to t star, but agent 1's is t star plus phi. It means that their intersection point, sort of the earliest possible date at which the bank run can happen, is strictly higher than t star. So let's just see why that is. So here's t star, okay, and here's the 45-degree line. Okay, here's agent 1's runtime. It's an increasing function there. It only intersects agent 2's runtime sometime later, so sometime above t star. Okay, and that gap, so let's just project that onto the 45-degree line and look over here. Okay, and that point I'm going to call t star plus the gap. I'm going to call the gap t double star. So that gap t double star is the bonus that the principal gets from having a second agent. Because remember, with the single agent version of this problem, the principal got t star for free and then a 1 minus lambda expected time after that. What is the principal getting here? He's getting t star plus t double star for free, and then a random time at which the second agent runs. What is the distribution of that random time at which the second agent runs? It's exponential with parameter lambda, because it's either on this branch or on this branch, but each of these are exponential distributions with parameter lambda. Okay? So each of these induce on the vertical axis, given the distribution on the horizontal axis is exponential, each of these induce on the vertical axis an exponential distribution with parameter lambda. So the principal's value from this problem, if we're just focusing on how long does it take before the second agent runs, it's t star plus t double star plus 1 over lambda. Okay, and so that's what I'm writing here. Okay, in fact, we could say something stronger, and what's written here is stronger than that. Okay, so we're asking, what is the probability that the time of a bank run happens before some given time t? Well, that's 0 if we're picking a time that's below this initial interval. And then after that, it's the exponential distribution with parameter lambda. Okay? Now, in fact, this probability for any given t, this probability is the minimum among all feasible mechanisms, among all incentive compatible mechanisms. Okay? So I'm going to briefly explain why in a second, but just let me interpret the result. Okay? So this says if you take any incentive compatible joint mechanism, this mechanism first order stochastically dominates it in terms of the date at which the second agent runs. Okay? And that's why I said that this mechanism is going to be optimal under any payoff function, okay? Because you can't do better than the individual optimum, which we're achieving on the margins, and you can't do any better on the simultaneously on the date at which the bank run happens. Okay, so I'm not going to write out the proof of it. The basic idea is the following. Okay, so if you think about the construction of this mechanism, the thing that made it work, the reason our hopeful approach worked out, and we didn't have to start thinking about trade-offs between individual optimality and the bank run date, was that with both of these two individually optimal mechanisms, in fact, with any individually optimal mechanism, the critical event, which is the union of the bank is distressed or the other guy has already run, it just winds up being the event that the bank is distressed. Okay? So that is to say, we can construct individually optimal mechanisms so that the higher order beliefs are already dealt with. Okay, they didn't wind up being a constraint. Okay? So the suggestive route to trying to prove that this is optimal by just considering a relaxed problem in which we just ignore that constraint. So let's think about a problem where these agents view themselves as being strategically independent. So agent 1 now only cares about the health of the bank. He could care less whether the other guy has run. Okay? Now, we know that the mechanism that I described works for that problem, but now we've just removed the constraint. So in principle, we might be able to find an even better mechanism that takes advantage of the fact that I don't have to worry about that constraint. The key idea behind the proof is that that problem is easy to solve. I don't have to worry about higher order beliefs. And the solution to that problem is the mechanism that I've given you. Okay? Or achieves the same, the value of that problem is the value that I've given you here.
I don't understand how that squares. So I understood this last time you said it, but how that squares with the answer to Dirk, namely that you could do better if you didn't have the IC constraint where I didn't worry about what the other guy did. I thought the problem with making correlation more negative is one guy thinks the other guy must have moved.
Because there's more to the incentive constraint than just did the other guy run. It's that if I know that our runtimes are negatively correlated, okay, then there's more information contained in my signal than just the beep itself. In particular, if a lot of time has passed, I can infer that you've heard a beep. Now, I could care less whether you've run, but the fact that you've heard a beep means the bank is insolvent. And I want to run if the bank is insolvent. Okay? This is just another way of saying that these things can't be too negatively correlated because they come from individual optimization of runtimes, and that has to be correlated with the same variable, the state. So I want to just say what I know about the multi-agent, the many-agent case, more than two. Okay? And it's not much, but it is a little bit. Okay? So for starters, I want to show you. So first of all, the problem is that this nice mechanism, which had the nice feature that it first order stochastically dominates any other mechanism and is also individually optimal, that property is not going to work for more than two. Okay? There is going to be some trade-off between individual optimality and the bank run. Now, if there's 3 agents, what does a bank run mean? So now I'll be flexible. I say I've got n agents, and there's strategic complementarity, meaning that agent I wants to run when he thinks that either the bank is distressed or some number k of the other agents have run, okay, with sufficient probability. Okay? And then the principal wants to avoid the event that k agents have run, or k plus 1 agents have run. Okay? So that's going to be the problem. And I'm not going to be, there's going to be a trade-off now between individual optimality and delaying the date at which that kth agent runs. Okay? So to warm up for a mechanism that deals with that trade-off, I want to describe a mechanism for the 2-agent problem where the trade-off is evident. Okay? So I'm going to show you another mechanism here which has the virtue of being symmetric. Okay? So the problem with the one drawback of the mechanism I described is I give a separate mechanism for agent 1 than agent 2, and the nice thing is it was deterministic. I'm going to show you a symmetric mechanism which is not deterministic, okay, where the runtimes are random, even as a function of the state change. Okay, and it works like this. And this is going to be something I'm going to build onto to develop a mechanism for many agents. Okay, so 2 agents. I'm going to randomly decide which agent gets one of the following 2 mechanisms. I'm going to randomly allocate the following 2 mechanisms to the 2 agents. One is just beep on. That means the agent is informed immediately when the bank becomes insolvent. Okay. The second one is a delay, but the delay is going to be of length t star plus t double star. Okay. And I'm not going to tell the agents which one is which. Okay, so each agent knows that with probability half they're facing this mechanism, with probability half they're facing this mechanism. So now if this mechanism is incentive compatible, it achieves the optimal value, okay, because the person who's going to run second is the guy who's got the delay. And how long is his delay? T star plus t double star. Okay, so I just need to show that this mechanism is incentive compatible. So I'll just sketch the argument for why. The issue is that if I'm waiting around and I haven't heard a beep, I'm asking myself, what is the probability that the bank is insolvent? Okay, it's still true that the other guy is running if and only if the bank is insolvent. I mean, running only if the bank is insolvent. Okay, so I just care about the probability that the bank is insolvent. Okay, so what is that probability? Well, if I have yet to hear a beep, the only possible way that the bank is not yet insolvent, that the bank is insolvent, is if it's I that have the delay. Okay, so I want to ask, what's the probability that it's me who's got the delayed beep mechanism at time t, conditional on not having heard anything yet, because this belief is going to be updated over time. And then at time t, what's the conditional probability that the bank has become insolvent, given that I'm the guy that has the delayed beep mechanism? The product of those is going to give me my conditional probability that the bank is insolvent. Okay? So the observation is that both of these probabilities are increasing over time, but then become constant when we reach the delay length, when we reach the time equal to the delay length. Okay? So here's why. Okay, so over time, if I haven't heard a beep, it's becoming more likely that the reason is that I'm the guy that's got the delay. Okay? And that's because it might have happened already and I didn't hear it yet because of the delay. Okay? But once we've reached that much time, once that much time has passed and time moves on, it's always, the key event is always that it happened in the most recent past of length delta. Okay? And that conditional probability is remaining constant over time. It's just like the old story. Okay? So this belief trends upward and then is constant at time delta. It's also true that the conditional probability that the bank has become insolvent, if I know I'm the guy with the delayed beep, is increasing over time and then is constant once we reach the delay. This is just the old delayed beep mechanism inference. Okay, so both of these are increasing and then constant at delta. So they reach their maximum when we get to delta. And so we want to find what's the value of delta that gets that probability exactly at the threshold p star. Because then I'll delay withdrawing until I hear a beep. Okay? And if you solve that problem, you get delta equals t star plus t double star. Okay? Okay, and so this mechanism is not individually optimal because one guy is running right away. So, in fact, we made use of the trade-off, but it didn't cost us. We just threw away surplus in some sense by making the mechanism individually suboptimal, but achieving the same value for the bank run date. But we're going to do this. We're going to do the same idea with many agents, and I'll just say I won't walk through the slides since I'm out of time. But what we do now with many agents is we just divide the many agents into two groups. One group is all going to be informed simultaneously exactly at the moment when the bank becomes insolvent. So they have beep on. The other group gets a delay. And we want to calculate what's the maximal delay we can give them so that incentive compatibility is satisfied. And it's going to be a calculation just like I gave before. Okay? Then we can solve for the maximal delay that keeps the incentive compatibility. And, it's a formula. Okay? But basically the formula says that what matters is the fraction. Think about the population growing large. Okay? So there's n agents and n is growing. Key is the fraction of agents that make up a bank run. Okay, so let's say a bank run happens when 2/3 of the agents have withdrawn. Okay, so each agent is ready to hold on unless he thinks 2/3 of the other agents have withdrawn. The bank wants to stop 2/3 of the agents from withdrawing. How long can the bank forestall that? Well, it's a function of that fraction. Okay, and it's that fraction. This should be some function of the fraction. Don't forget about these numbers here. Symbols here. And so, for example, if that fraction is 100%, this turns out to be approaching infinity as the population grows to infinity. If the fraction stays bounded, then this converges to some bound, and it's strictly increasing in the fraction. Okay? So the principal gets, when we went from 1 agent to 2, he got that T double star bonus. Go to 2 agents to 3, if you keep the fractions, there's another bonus. And then these bonuses result in a series that converge to some number, and that's the value in the limit. All right, so I think I'll stop.